Welcome to the concept of design equation for ideal reactors. Before we go into deep, let's have a look at what we studied in the previous lectures. We performed so many calculations and so many derivations for the interpretation of batch reactor data, as well as those who are required. The equations are required for designing the polymer reaction reactors plus polymerization processes. And all these things are in situ with the various kind of a polymerization schemes, maybe the solution polymerization, maybe the emulsion polymerization, etc. Now, in this particular lecture, we are going to study about the concept of general mole balance equation. All these equations are of course the mathematical equations. We will discuss about the design equation for any ideal batch reactor, mixed flow reactor, ideal PFR, semi-batch reactor, etc. We will have a basic concept of space time and space velocity. You know that both the things are extremely important for handling the reactors, various kind of reactors, those who are in question with the polymer reaction engineering. We will develop several design equation for single reactor system using batch reactors. So let's have start with the general mole balance equation. Now you see that here we have just given a block diagram about the general for the prediction of mole balance equation. So for mole balance of any species I on the system volume, where I represent a particular chemical species. Suppose a number of species are taking part in a particular reactor, and there may be different species like A, B, C, D, etc. Now here you can represent any individual species like I, maybe J, K, etc. Now this is if you talk in terms of reaction engineering, or if you talk in terms of thermodynamics, this is the microscopic level apart from the macroscopic concept. So let's have that this mole balance, we are in the interest of any species I in terms of developing the mole balance equation. So anything which is participating in this particular reaction mass, there are two streams. One is that input stream, another one is output stream. So if we consider a system volume related to the reactor, which is usually enclosed by boundaries in chemical reaction. Now as you know, then thermodynamically the boundaries are three different types: isolated, open, and permeably. Now here then if you see that this particular reaction where the system volume is having say V, and you are having the stream that is FIO, that is the start of your ith species, and after say time interval t and crossing the system volume V, it is having the flow rate of Fi. Now the mole balance equation you can develop with respect to the chemical species through the system volume, and if you are having time t from t is equal to 0 to t is equal to 1. So the rate of reactant I usually into entering into the system volume minus the rate of reactant I out of the system volume. This is then the rate of a generation of species I within the reactor due to the chemical reaction is equal to the rate of accumulation of reactant I within the system volume. Now you see in this particular mathematical equation we have encountered all kind of approaches, that is how much ith species being consumed in due course of time during the reaction, how much rate is there of reactant I into the system volume which is entering and which is going out. So we have considered all approaches of species I in that particular reaction stream. Now if we try to put this entire scheme mathematically, then we can write the mole balance of chemical species like this, that Fi naught minus Fi, which is this one, plus Ji naught, that is the rate of a generation of a species I within the reactor due to the chemical reaction, and it is I naught upon dt. So the rate of generation of a species I usually given by Gi is equal to V. Now, if we consider that V is the system volume in the reactor, which is usually divided into n sub-volume due to the formation of various species in I in the reactor, and sometimes it is different at every position of the reactor volume. Sometimes you may need to have a sequential approaches, like one output is the input of another one, and sometimes these things are integrated within the specified volume. So, if we talk about the total generation of species I in the system volume, it is usually sum of all generations in each of sub-volumes. So, if we consider that the total volume which need to be divided into n different type of sub-volume, and the rate of a generation of a species I at any point of time or any position 1, that is sometimes referred as delta V1. So, this can be represented as delta GI1. Now, if there are Ni systems, these are the system sub volumes, then the total rate of generation is summation I Now, this is the total rate of generation for this particular system. Now, with the knowledge of integration, and sometimes need to take the appropriate limit, like n tends to infinity and delta V tends to 0. This equation which we discussed previously, regarding the total rate of generation, it can be written as J nu. So, this mole balance equation, again, if we wish to rearrange the things, and if we wish to rewrite that particular equation, it can be rewritten as, with respect to the flow rate, now this is the final mole balance equation and the designed equation for different reactor types. Now, let us have a consideration to different type of ideal reactors. Now, here the ideal batch reactor, the concept of ideal batch reactor, that we have to design the performance equation for homogeneous reacting system, or for single fluid reacting in the ideal reactor, which is further being used for isothermal or a non-isothermal equation. If you recall that in the previous lecture we discussed about the equimolar and a non-equimolar type of system. Now, in batch reactor, the reactants are usually charged, followed by, if you see here, followed by mixed thoroughly or rigorously, depending upon the scenario, and react for a certain period of time, and then discharge after completion of the reaction. This is a basic definition of your batch reactor. Now, as the composition of product changes with the time in the reactor, there is an unsteady type of operation and referred as unsteady state operation. So, the composition throughout the reactor is remaining constant at any particular point of time. There are various applications associated with this type of reactor system. It is used for the testing of a new process which is not yet fully developed, because see, our benchmarking is this one. It is used for the manufacturing of all kind of expensive materials. Sometimes because of the limitation in the continuous type of a reactor, this is more feasible. For processes which is difficult to convert into continuous processes. There are various advantages and disadvantages associated with this type of reactor system. It has advantages, that being high conversion of a reactant after leaving the material in the reactor for a longer period of time. but there are certain disadvantages associated with this reactor, that it requires higher labor cost for charging, discharging and cleaning per batch, because you need to put the entire mass over here and then you need to discharge the things. So thereby it creates a lot of economic burden to the system. There is a variation in the product quality per batch, and sometimes there may be a chances of formation of stagnant zones within the reactor mass. That is why it is best suited for small scale industrial operation. Now let us have a look about the design equation for batch reactors. Usually the inflow and outflow of the reactants or a product, they are not allowed during the process of a reaction, as you refer to this particular batch reactor. So if we say that Fi naught and Fi they are 0 at the generalized mole balance equation which we developed in earlier concept. So the general mole balance equation we can write as which is dNi upon dt, or so this is the general mole balance equation. Now the reacting material is perfectly mixed throughout the reactor. So there is no change in the rate of reaction in the reactor and volume. Therefore, the required performance equation in the batch reactor is usually given by so this is our required performance equation, which is quite useful for the system. Now let us have a look about the various design equations for ideal reactors. So the design equation for any ideal mixed flow reactor or CSTR continuous tank reactors, sometimes referred as this one. So it is used for the liquid phase reaction and operated under steady state condition, and this condition prevails that the composition of the reactant does not change with respect to the time. And it is also known as a continuous fluid flow stirred tank reactor, and ideal stirred tank reactor, back mix reactor and a mixed flow reactors. So these are the common names in the reaction engineering. Now there is a perfect mixing of a material throughout the reactor. Therefore, the concentration and the temperature, they are supposed to be constant throughout. So if we take the temperature and concentration in the reactor is same as in the exit stream, this is my exit stream. Therefore, the flow within the reactor is mixed flow, and the reactor is called the mixed flow reactor. It is operated under the steady state condition, that is dNi upon dt is equal to 0. So accumulation is 0, and the general mole balance equation can be written as Fi, because the accumulation term is in this case is 0. Now due to perfect mixing in the reactor, there is no change in the rate of a reaction. Therefore, the design equation for MFR or mixed flow reactor can be written as or Fi upon now this is the required performance equation for MFR or CSTR for finding out the volume required to change in the composition from initial molar to the final molar conditions. Now let us have a look about the PFR, the plug flow reactor. Now this is the simplest diagram of the plug flow reactor. This is a special type of a chemical reactor which has a cylindrical tube like structure operated at a steady state and it's very useful for various gaseous phase reaction. When you require the gaseous phase reaction need to be performed, then it's a very useful reaction for this. Now the concentration of the reactant consumed as it moves forward into the tubular reactor in the axial direction. Now there is no radial variation in the velocity profile, concentration, temperature in the reaction rate. Now there are variation in concentration, rate of reaction and a temperature in axial direction only. If you see that this is the typical anatomy of general mole balance equation of a PFR. Now here if we wish to write the design equation, then the starting point is that mole rate of any reactant I at the entrance. I am drawing this PFR again at entering. Then the mole rate of a reactant I at the outlet, that sometimes it may be V plus represented as V plus delta V, plus molar rate of generation of a species I within this delta V due to any kind of a chemical reaction, and last is the molar rate of accumulation of reactant I within that particular change in volume. So the general mole balance equation we can write like this, not at V minus Fi at V plus delta V. Now if we divide both the sides with the delta V and rearrange the things, then we have upon delta V. Now if we take the things like delta V tends to 0, then tends to 0, delta V, or this refers to dFi upon dV. Now this is the required differential form of performance equation for any PFR. Now let us have a due consideration to the space time and space velocity. Now this at time t usually is used for the measurement of a performance in the batch reactor. Similarly, space time and space velocity, they are used as the performance measure in any kind of flow system within the reactor system. Now space time, this is the time required for processing of one reactor volume of feed in a flow reactor at some specified temperature and pressure and other conditions of the reaction. Now it is usually represented as tau and has a unit of time. Now mathematically, if we wish to represent this space time, this is space time tau is equal to volume of reacting fluid, that is V, divided by volumetric flow rate of fluid. So tau is equal to, and here this nu naught is equal to Fa naught upon C. Now this is the volumetric flow rate. This is equal to molar flow rate unit and represented as mole per second, and Ca naught is the initial concentration of reactant A, having the unit of mole per liter. Now another good concept is the space velocity. This is usually the reciprocal of space time, that is the number of reactor volume of feed processed in unit time at some specified conditions, may be related to the pressure, temperature, etc. And it is represented by small s and has the unit of time inverse. So mathematically we can put forward like this: space velocity, space time, or F A naught so unit is secant inverse. So this is the space velocity. Now space time, sorry, now in general way we can say that if there is a space time of say 5 hour for a reaction to complete, then it means that there is 5 hour required to process one reactor volume feed. And if we say that the space velocity is given by 5 hours inverse, that is 5 reactor volumes are processed in an hour under the specified conditions of the reaction with respect to the temperature and pressure. Now let us have a consideration of a semi-batch reactor. Usually there are various features associated with the semi-batch reactor. As you see that here in the figure, there is an input and usually output is restricted. So this is an unsteady state type of operation and primarily being used for various liquid phase reactions. So it can be used in two phases, maybe the gas liquid reactions where the gas is usually bubbled or sparged through the liquid, and it used to enhance the selectivity of liquid phase reaction. Again there are various advantages and disadvantages associated with this semi-batch reactor. Now it has advantages of controlling the reaction rate and temperature, and it has a concept of minimization of unwanted side reaction by maintaining the low concentration of reactant. So this type of thing you can easily control within this semi-batch reactor. There are a couple of disadvantages within the semi-batch reactor, that it again requires the higher labor cost for charging, discharging, cleaning per batch, etc. There is a variation in the product quality per batch because it all depends on a batch type of a scenario. Therefore, based on these two disadvantages and a couple of advantages associated with it, it is best suited for small scale industrial operation. Now let us have look about the different type of semi-batch reactor. There are two type of semi-batch reactor. Usually they are used to enhance the selectivity in the liquid phase reaction. So let us consider this particular general chemical equation which we discussed priorly. A plus B is equal to P plus R. So the type 1, if reactant A is added to the reactor and B is already present in the reactor. So this kind of a reactor, just give a figurative approach, B is present and you are adding A into it. So this kind of a reactor is used to minimize the formation of any kind of unwanted product, sometimes may be referred as R, to control the reaction rate and the temperature of the reaction. Now couple of examples of this particular type of reactor, that is ammonolysis, hydrolysis, chlorination, etc. Now another type of reactor is that the reactive distillation usually is the another type of semi-batch reactor in which reactants are charged simultaneously to the reactor and vaporized product is withdrawn continuously from the reactor. The example of these particular reaction are acetylation reaction, esterification reaction, are the best suited example for such type of reactor, where water is continuously being removed from the reactor so that you can maintain the appropriate condition within the reactor. Now let us have a look about the various design equations for a single reacting system under the batch reactor. Now if there is a reactant A consumed to produce P in the previous equation, and initially if say that Na naught moles of the reactant A is charged into the reactor, say after some time T, if the required conversion to be achieved, and this may be referred as Xa, then the remaining mole of reactant A in the reactor, it can be calculated by the basic mole balance equation, and that is Na is equal to Na naught Xa. Now here this Na naught is the initial number of moles of A, and this Na naught Xa moles of A consumed within the reaction. So this equation can be represented as 1 minus Xa, and the differential performance equation for this ideal batch reactor can be represented like this. Now for disappearing of reactant A in the reaction, the performance equation we can write like this. Now here the negative sign before the rate of and accumulation are for the disappearance of reactant A, as I discussed previously during the reaction proceeds, and this convert into the product P. So the value of rate is obtained from the rate law, and from accumulation in terms of conversion, differentiate the above equation, this equation for remaining moles of reactant A with respect to time. Now accumulation, if we talk about the accumulation term in the form of conversion is given as minus dNA and dt, or now then the differential equation for the batch reactor in terms of conversion can be written as minus Ra Na naught Xa dt Now, if we integrate with the and rearrange the things, keeping in an eye over the initial conditions at t is equal to 0, and at this point x is equal to 0, and for t is equal to t, and at this point the x is equal to x, then we can represent like this. Now, this is you can say the required performance equation for batch reactor at constant time. Now, sometimes you need to put the graphical representation of performance equation for the batch reactor, and the governing equation for this one is and t is now if you wish to plot the things, this is Xa and this is 1 upon Ra. It is very common thing. Now, this area under this particular curve like this is equal to T upon Ca naught. Similarly, if I go for one upon Ra versus Ca, now here this is the Ca naught, Now, the governing equation for this particular type of scenario is your C minus RA. So, by this way you can predict the situation. Now, for varying volume system, if we put the putting the varying volume relation in the rate law, the performance equation we can write like this. Now, if you recall the previous plot, and A naught this is T is equal to Na naught upon V naught 0 to xa, because T is equal to 0 and xa is equal to x, then dxa upon 1 plus epsilon A xa into minus Ra, or T can be represented as Ca naught 1 plus epsilon A xa minus Ra. So, this is your performance equation for this particular situation. Now, in this particular lecture, we discussed about the various design equations for various kind of reaction system, and we developed various performance equation attributed to all kind of reacting system. Now, if you wish to have further reading related to these particular concepts, you can have a look of these references which are enlisted in this particular slide. By this way, thank you very much